So we're talking about solutions, and we'll talk about a little bit how they're made, and we'll talk about how to calculate their concentration. But what's the big deal? Well, the big deal, I guess, is if you screw it up, it could be lethal, right? That happens in these articles here. For you, you screw up your concentration calculation, and I guess it could mean more time in the lab or a worse grade. But let's start with solutions. And solutions are, well, they're just mixtures, right? But if a solution is supposed to be completely the same concentration throughout, the word was homogeneous. And let's start with the difference between a solute and a solvent here. Let's see. So you can't really see the solution, the solvent, but if I dump enough of this stuff in there, you might be able to see it. There it is, right? And we can kind of monitor the concentration and have it calculated. So what's this is supposed to be water that we dumped in that we started out with. Alyssa, in this example, what's the solvent? Yeah, the liquid that we dumped it into. The solute would be the drink mix. But pretty much everything in life is a solution. They're all mixtures. And the way to tell the difference between a solute and a solvent is you have all these things that are mixed together. And you list them all out. You pick out the one that you have the most of. And Bowdy, that's always called the solvent. That's how you do it. You see which one you have the most of, and that's the solvent. So, because it may not be as obvious as this. Okay. What if Cameron, how about if I open this little valve here? Open this little valve and let some stuff pour out. What's going to happen to the concentration?
It'll stay the same.
Stay the same? Everybody agree? Yeah, right, should. How about if I open this valve, though? Mia, open this valve. Will it go up or down?
Down.
It'll go down.
Down.
It'll go down. It's the D word. You are what to the solution? You are diluting it. Yeah. Definitely drops like a rock. Okay. What is going on at the atomic level when salt dissolves in water? Okay, let's take a look at this. So before we let the little animation go here, we said salt dissolving in water stuff. Where's the salt? Yeah, the big cube looking thing. And the salt was supposed to be sodium and sodium chloride, sodium ions, chloride anions, right? Sodium cations, chloride anions. Andrea, what are these things floating around? Water molecules. Anessa, is water a bent molecule? See if you remember the talk. Is water a bent molecule? Right? If it was linear, the hydrogens would be lined up, right? It'd form a straight line like a pencil. Right? It'd form a straight line like a pencil. So is water look bent to you? It should look bent, right? Okay. Is water a polar molecule? Anybody? Is water polar? Yes. So what's the consequence of that? If it's water is a polar molecule. Enrique, water is a polar molecule. So what does that mean?
Water is a polar molecule?
Yeah.
Having to do with the two oxygens and the hydrogen. So
Yeah. Water. Polar meant there's a little partial negative, a little partial positive, right? So where's the partial negative go? On the oxygen, because it is more, what's electronegative is the word, it's closer to F. So there's a little partial negative, oxygen's partially negative, down here by the hydrogens it's partially positive. That's the only hint you're going to have to figure out which one is which here. Because if this is dissolving, this sodium chloride crystal, notice how it's kind of cubically packed, one of those cubic packing things. But as it pulls off the sodium and the chloride anions, how the water molecule is oriented is the only hint you have as to whether it's the sodium or the chloride anion. I'll give you an example here. Let's pull one off. This is supposed to be sodium chloride dissolving. See how this is getting pulled off? Okay. Let's stop there. That gray sphere must be, Megan, the chloride anion or the sodium cation. Remember, anions are negative, cations are positive. Anion? Now, remember the O's we said were what? On water, they're supposed to be negative. So they should all be oriented towards something positive. So that means that gray sphere must be something positive. It's going to be the cation, which is sodium. Okay? So this is a sodium ion. So this is what it looks like for sodium in water. Okay? Keep this going. This is what they call hydration. Now here's a chloride anion being hydrated. Right? All the hydrogens are locked around it. Okay? So when we were, we've been lazy for a while, right? These guys are all hydrated. They're all solvated in water. They're surrounded by water molecules. And we're supposed to illustrate that by writing a subscript what on every single ion in water. And write, not liquid, because liquid means it would be a liquid. Aqueous, we're supposed to write AQ. Every single time we're supposed to, because you can't stop hydration. But we never did, right? But that's how you're supposed to write the sodium cation in water. So make a quick sketch here of what sodium looked like if it's hydrated in water. Right? So have your sodium ion, then orient the water around it so that it's hydrated. So orient those bent water molecules around it so it's hydrated. So I could maybe something like this. How would you draw the water molecules? Kenneth, how are you going to draw the water molecules?
With the oxygen touching it.
Yeah, with the oxygen's touching it. And just have the H's pointing out. Just draw a bunch of them. And in fact, you keep drawing these things. They get into shells. It gets really complicated. There's a lot of chemistry in solvation. Okay, but there's going to be a lot of waters. Okay, the higher the charge, the more strongly they're going to be solvated. From the sketch the chloride anion. So do the same thing. But Kendall, now how are you going to draw the water molecules?
With the H's.
Yeah, with the H's. Kind of surrounding it. The oxygen's all pointing away. And let's draw a bunch of them. Okay? Draw as many as you can squeeze in there. Jose, see how we're already lazy? We should be writing AQ on these things, especially today. But iron 2 and iron 1, Jose, are in water. Which one would be more strongly hydrated? Fe2. Why? He's right. Why? It's more positive, higher charge. Yeah, so there should be a stronger interaction. Right? Okay, so we're making solutions. You add a solute to a solvent, have it mixed up so it's in homogeneous concentrations, evenly spread throughout, you've got a solution. But you keep on adding the solute. You keep on adding the solute until you get something like this. Right? And it just sits, this has been like this for months. So in the solution, it can't dissolve anymore. So this is a what type of solution then? What would they call this, Audrey? This is a, starts with an S. Saturated. Can't dissolve anymore. Saturated. Okay. And you'd think that, man, this is just sitting there, just like a lump sitting on the bottom. There's nothing going on. But there is. At the microscopic level, there is. Let's take a look at what they're trying to illustrate to us. First off, they said that it's an equilibrium. Then they said it's dynamic. I'm going to pause this before it even starts. When we said I already have the answer there. When we write a reaction, these are called what? These are called what? Reactants go to products. And we always draw one arrow. Another lazy thing. We're not supposed to, because over time, you know, this stuff is forming this stuff, but every single reaction has a reverse. Now, sometimes you should probably draw a little dinky arrow because there's not very much. It doesn't go backwards very much. You almost get all product, and that's typically what we're used to. But a lot of reactions, no. I mean, you get a lot of going backwards. But the point is once the rate of going forward equals the rate of going backward, it's at equilibrium. So it could be evenly distributed. It could be, man, it could be this way. You could hardly get any product at all, but it's at equilibrium already. So the rate of forming products is the same as the rate of forming reactants. So we hardly ever draw these different sized arrows, though. We're supposed to draw just double arrows. We're supposed to every single time. That's the dynamic word. Okay. When we dumped in that at the beginning, we dumped in that drink mix into water. I mean, there wasn't any saturated solution to go on. It just all formed. It all dissolved. But if you keep dumping it in, you will reach a dynamic equilibrium because there's going to be some solid here, and then you can't stop the dissolving. You can't stop the precipitating. The rates just become the same. And that's what this animation is trying to illustrate. Let's see if it can do a better job than I tried. So you've got the water molecules and the crystal, and it's not a very good animation because this stuff should be flying around. So you've got these solvated, those are the solvated chloride anions and solvated sodium ions floating in solution, and right, they're precipitating out at the same rate that they're getting pulled off. So the animation doesn't, I don't know if it does it fast enough. It should be doing it really fast. It's building, but it's not pulling it. Oh, it pulled some off on that side. But that's the idea, that it's dissolving at the same rate it's precipitating. That's a dynamic equilibrium. The solution's saturated. You can't get any more to dissolve. So it looks like the solution is nice and steady, but there's dynamic equilibrium going on there. The surface is continually being refreshed. Where did the 3 and the 2 come from? Can you see that? The calcium phosphate? Andromeda, where did the 3 and the 2 come from? Do you remember? The charges, right? We just did the switcheroo thing. Right? The calcium's a +2, that came down there. The phosphate was a -3, that went down there. Just see if you remember that stuff. Okay. So we've got a saturated solution now. Then the book says, oh, there's also a supersaturated solution. How can I saturate, oh, Alyssa, how can I saturate a sponge? Here's a sponge. How could I saturate a sponge? Yeah, dip it in water for a while and pull it out really slowly and carefully. Don't squeeze it, right? Okay, so then it's saturated. Supersaturated, Cameron, must mean what? It's not even, it's not even possible, right? Because supersaturated means it has to hold even more. Right. But we pulled it out. It's holding as much as it possibly can. So you can't do that with this. But solutions, you can get them to dissolve more. Right now, this solution on top of the calcium phosphate is saturated, right? Because it's been there forever, so I know it's saturated. But how could I get it to dissolve even more of this solid? What could I do to this? Make the solution what? Anybody? Hotter. Make it hotter, right? Then it will definitely start dissolving more. Make it even hotter, dissolve even more. So that's the trick to getting a supersaturated solution. Now, it's a very touchy thing. So you heat this up. We take this, we heat it up. It'll dissolve more, right? And then what you got to do is take off the liquid, and while it's hot, run it through a filter or something, right? So you get just the solution. But you got to keep it hot the whole time. And then don't shake it, just let it set. So you filter it, you might end up with something that looks like this. And then you let it set, and it's hot. Just let it cool down. Don't shake it, don't jiggle it, nothing. And then it's a very unstable situation because it's dissolved more than it's supposed to be able to dissolve. So it's not a very easy thing to make, but it's a cool thing to do. So that's why I'm going to show you the video instead of actually making this stuff. Let's see if I can. There, it looks better this way. So let me pause it here first, because what they had to do is they took this sodium acetate, they dissolved it. Here's the sodium acetate. They dissolved it, right? And then they heated it up so it could dissolve even more, right? And then they filtered the solution while it was hot and let it cool. So now they can't even jiggle this, because if they did, something's going to happen. So they're not going to jiggle it. They're just going to add a hygroscopic nuclei. They're going to add something to start the crystallization, for everything else in the solution to grab onto and come out of solution. So that technical word is hygroscopic nuclei. But the trihydrate. And in the crystalline form, there's 3 waters for every 1 sodium acetate. So their hygroscopic nuclei could be anything. They're just going to take a crystal of the sodium acetate and drop it in there. They could have just jiggled the thing, but then it wouldn't be so cool looking. So everything in that supersaturated solution, it just grabs onto that hygroscopic nuclei and just starts precipitating out. It's solid. I mean, it's an extreme case of supersaturation, but it works. So you can take the flask and lift it upside down. Nothing's going to come out of there. Did you ever hear of Bill Nye, the Science Guy? Yeah? I like Bill Nye. Okay. I think it's kind of interesting that we can put guys on the moon, but we're not so sure how water goes higher than 23 feet in a tree. We're not so sure how tornadoes work. We're not so sure where the hell is this hurricane going to go. We're not so sure about a number of things, and one of them is precipitation. We believe that you get this, again, you have to have these theories, the Bergeron process, the theory, but the idea is you have this supersaturated region of air. This is for precipitation. You have a supersaturated region of air, and then you get some little particles of water or something to go through there, to get blown through, and then it collects on, right? 'Cause it's supersaturated. More water will collect on until this finally gets so big and heavy it just falls, and if it's cold, it'll freeze, rain, snow, sleet, whatever the case is. So what I want to show you here is how to make a cloud. And I saw this on Bill Nye the Science Guy. So you need air. So we've got a bunch of air. Okay? And I need water. So I need water vapor, but I need it to be supersaturated. So I definitely have water vapor in there now, but I can get a lot more by doing this. Okay? And now that I dumped liquid water in there, did I also add water vapor? No? If it's another dynamic equilibrium idea. If we just leave and come back on Monday, this is going to be evaporated totally, right? But if I cap it, right, it's going to stay there. So that means that there's an equilibrium going on between evaporation and condensation. So it's dynamic. You can't stop it. And what's interesting to me is how fast it happens. I mean, it's just by capping this, it's really humid in there. It's saturated. It's really humid. It's not super saturated, but it's saturated. It happens really fast. So, okay, but I can get it super saturated by cooling it down, because then the air isn't supposed to be able to hold as much water. So how am I going to cool it down? I'm going to fill this with air and just let it shoot out of there, let it expand. Okay, that's how I'm going to generate my supersaturated region. And hopefully there will be something in the air to serve as hygroscopic nuclei for my cloud. Well, you saw, maybe you could see a little bit of a tinge of cloud, but not much. We need more hygroscopic nuclei. So I'm going to add some smoke and let it serve as my hygroscopic nuclei. Get the match going. And when I drop it in there, there'll be a little puff. I don't know if you saw it, but there's a little puff of smoke. Try it again. There's a cloud. Okay. But take a whiff. What does it smell like? It smells like burned matches, doesn't it? It smells like smoke. Is this what our world smells like to generate clouds? Definitely not. So there must be something else serving as hygroscopic nuclei to generate our clouds. It has to be a hunk of matter that when it goes through the supersaturated region, everything will collect around it. What could it be? I'll give you a hint. 3/4 of our planet is covered with this stuff. 3/4? What type of water? Salt water. Okay. Sun's beating on it, dissolves. Where's all the salt go? It just gets into the air. The argument is that inside every single raindrop, every single snowflake, is a very small crystal of salt. Why can't you taste it then? Ugh. What is too small? The concentration. The concentration is too small. Any water that you drink, it is not pure. And it shouldn't be. That wouldn't be very healthy. The stuff you want, you want that stuff in there. Calcium and iron. And you want it to be the pH that it's at. Okay. So referring to concentration, we need to understand or apply 4 ways of calculating concentration. So there's 4 of them up here. And even the units are there. Like here's big M. So that's molarity. So you might see a number like 0.18 big M. supposed to say 0.18 molarity, or 0.18 molar is the word, right? Here's another unit, little m. So if you add 0.18 little m, then you're supposed to say 0.18 molality, or 0.18 molal, right? And then you have mole fraction and mass percent. But here's the definitions, and I give them to you all. So in the 4 ways of calculating concentration, let's treat them, Alyssa, as mathematical equations. So each equation here has how many things that can change? How many variables? Well, yeah, 1, 2, 3. There's 3 things in every single equation. That means every single homework question, Bowdy, is going to give you how many variables? 2. Otherwise, it's not going to be a question, right? They're going to give you 2 and you solve for the 3rd. That's what you do in every single one of these. I think the only twist is this, Cameron. To make solutions, right, you usually mass out the solute on a balance. What are the units on that balance? Grams. Okay, now grams works up here for mass of solute, but these other ones, look at this, moles. They want to know how many grams of solute there are so that you mass it out and make that solution. This equation isn't going to give you grams. It's going to give you moles. So if you solve for moles, Mia, how are you going to get grams out of that? Not mole bridge. It's not a reaction. Molar mass, right? You have to use molar mass to convert moles into grams. So a lot of these questions are going to be 2 steps. No big deal. Okay. I think the only other part to remember is you've got, let's say you wanted to solve for this one, the one on the bottom. Pick one. The total liters of solution. Mathematically, how do you solve for that again, Steph? Yeah, we bring the total liters of solution to the top and the molarity number to the bottom. Remember doing that diagonal thing? That's all you got to remember, right? These 2 interconvert and those 2 interconvert. Okay, that's how you move stuff around. So let's try one of these. How would you prepare 250 grams of an aqueous solution that is 10% sodium carbonate by mass? So Andrea, we're probably going to use which one of these 4 equations? Yeah, right? So that's not so bad. So that's kind of obvious. But let's start out with the answer, because it's how would you prepare? So you have to write a sentence here. I'm going to just give you a template here. Add blank grams, or no, let's not add. Let's use the word 2. 2 blank grams of sodium carbonate. Add, what's the solvent? Right, because sodium carbonate is my solute. What's my solvent? There's only one word in there that gives you the hint. It's aqueous, Anessa, so that means the solvent is water. So to blank grams of sodium carbonate, add water until blank grams is reached. Maybe on the balance or something, right? So you keep adding water, Enrique, until you reach how many grams? 250. So there's really only one part that we got to figure out here. That's the grams of the sodium carbonate. And Andrea already told us the equation. So let's copy that equation down. We've got mass percent mass of the solute all over total mass times 100 or something. Okay. So Megan, what numbers should we plug in here? How's this going to work?
10% would go under mass percent.
Yeah, the 10 goes under the mass percent. Good. Then what?
250 grams.
Yeah, I agree with that. Yeah, X on top. And don't forget the times 100. Okay. Kenneth, how are you going to solve for the X? Tell me what you'd plug in your calculator. One big step, what you'd do. What would you plug in first?
Plug in the 100 on both sides. Or would you multiply 250 on each side? Because, see, the way I did it online, it was just like 10% of 250, so it's just 25.
Yeah, the answer is 25, but it's going to be more complicated. I got to change the number so you can't do it in your head, right? Yeah, but let's pretend you can't do it in your head, right? Let's change them right now, and you can't do it in your head.
So yeah, let's just divide by 100.
Yeah, what I'm driving at is for the homework. This is what I'm really driving at for this. Is you do everything in one step. You've already shown your work by writing this. Your next thing that you should write is something equals X. And you do that by seeing what to do with everything on here. You start with 10 in the calculator. Take it times 250, take it, divide by 100, hit equals, and you are done. That's how you handle these. It's so much healthier. One big step. And then you're right, you get 25. 10 times 250 divided by 100, you're going to 25. So the answer's 25. Okay? So I guess there's two ways to answer it. You could say to 25 grams of sodium carbonate, add 225 grams of water. That would work too. But okay. How about this one? How many grams of hydrogen bromide are in 25 mils of 0.18 molar hydrogen bromide? Kendall, which one are we going to be messing with?
The molarity.
Molarity. Okay. Jose, now what? Okay, what would you plug in for what? 0.18 for big M. That's not moles, that's molar, or molarity. Okay, what else are you going to plug in? Andromeda, there has to be one more thing. Liters is going to be what? Yeah, we got to convert it. Okay. How many mils in a liter? Yeah. Where does the number go? The bottom. The number always goes with a prefix except for which prefix? Kilo. The number is always going with the prefix except for kilo. And the number is how many? 1,000. 1,000. So you move the decimal place, divide by 1,000, or move the decimal place over 3 places. Right. So that'll be our liters. Okay. Solve for your moles. I think it's just see what to do here. See if you can finish it. Solve for your moles. Then Mia told us how to get to grams. Do you remember what you said, Mia?
Oh, I said the mole.
I know you said mole bridge. Molar mass, right. Alyssa, I'm lazy. What's the molar mass of hydrogen bromide? No, you don't know? Huh? Is it 81? Everybody get like 81? All right. So final answer, you got what, Bowdy?
0.362.
Anybody else get 0.362? We're good? Okay. Somewhere around 0.4, a little less. Okay. So now we're getting to the point where this is the only calculator you can use on all quizzes and exams. So class time on Monday, you come in to take the quiz, you got to have this. If you don't have one, you know, you got to, remember I gave you one? So, okay. So let's try the next one. See if you can figure out how to solve it. See if you can pick out the right equation. Figure out how much water has to be added. Recognize the little m. So that really tells you the equation you got to use, right? And sometimes I think it helps not even to write the words solute and solvent and just write in what they are. Like instead of writing solute, I could write what? Instead of writing solute. C6H12O6. Instead of writing solvent, just write H2O. Right? And I think that might make your life a little bit easier. It might help you to see what to do. It might, I don't know. It'll definitely tell you what the units are of your answer. Mia, what units are you going to come up with here for your answer? For how much water? What would be the units of your answer? They want to know how much water. And this is your equation.
Oh, we're doing kilograms.
It'll be kilograms will be your final answer. Kind of weird way to give answer, but who cares? They didn't. They just want to know how much. So you'll end up with kilograms of water. That's okay. Anybody not sure what to do? So it's got to be little m though, not big M, because big M is a different one.
Oh, yes, sir.
Right. So yeah, we're going to have to find the molar mass of that thing so you can get it into grams. Andrea, what did you get for the molar mass for that thing? Molar mass of fructose. 180.18. She got 6 carbons, 12 hydrogens, and 6 oxygens to add up to be 180.8. Anybody else get that? Around that? Good. 180.8. And then, so that's how many moles? What is it? 1.
9.71 times 10 to the -3.
Okay, so there's our mole number. So you'll end up with the equation like 0.125 is 9.71 times 10 to the -3 all over x or something, right? And out of that, we better get kilograms of water. How do you do that one step on your calculator? What are you going to do? Anybody see it? What would you plug in first? Good. Plug in that 9.71 times 10 to the -3, and then divide it by 0.125. If you can see that, and just jump from here to here, you're doing exactly what I'm trying to get you to do. No intermediate steps, right? Homework will be faster, easier, and much less frustrating, and you'll get the right answer much more often.
Does water come out to be kilograms?
Yeah, because that's what's in the denominator. We're solving for our x, which is kilograms of water. And they didn't care what units, so we'll just leave it in kilograms. What did you get? 0.07. Anybody else get 0.07?
Yes.
Excellent. Okay. So maybe you can, we have time, maybe you can set up this last one. See if you can set it up. And then we'll call it a day, and you have a whole weekend to run around in and do Gen Chem homework. Man, we're really out of time. So to do this, this 45 grams needs to go where? Convert it to what? Well, that's of the chloroform, though. Convert it to kilograms, because that's the solvent. So convert that to kilograms and plug it in down here. Yeah. And then here's our M. That'll go there. Exactly. We'll multiply that M by our kilograms We get our moles and then just use molar mass to get it into grams. What would be your answer for number 3, then we'll let you go? Magnesium or aluminum ion?
Aluminum.
Because it's more positive. Good deal. So have a good weekend.